Welcome back to the deep dive. Today we're jumping back into electromagnetism. Remember last time we handled light moving through gases? Pretty straightforward stuff. Atoms far apart, not really interacting.
Exactly. That was the, let's say, simplified case. But today, we're tackling the much richer and frankly more complex problem of light in dense matter. Think solids, liquids, places where atoms are packed right next to each other.
Right. So the mission today is really figuring out how that density changes the whole picture of optics. How does the matter itself modify the light?
Precisely. We want to bridge the gap between, the tiny scale of electrons jiggling inside atoms and the macroscopic thing we actually measure, the refractive index, another.
It sounds like it's all about interference then. The original light wave plus all the little waves coming off these wiggling atoms.
That's the heart of it. Refraction isn't just the incoming light bending. It's the result of this incredibly complex dance between the original wave and all the secondary waves generated by the material. And density is key.
Okay, so let's start at the beginning. An atom sits there, light wave comes in. How does it make the electron wiggle? What's our model?
We use a classic, very powerful analogy. The electron is like a little mass on a spring bound to the atom's nucleus. Simple harmonic oscillator.
Ah, the old reliable oscillator. So the spring is the force pulling the electron back if it gets displaced.
That's the restoring force, yes. And then the light wave's electric field, adiol, that's the driving force. It's oscillating, so it pushes and pulls the electron back and forth.
Okay, restoring force, driving force. Is that it?
One more crucial piece, damping. We need some kind of friction resistance. It's proportional to the electron's velocity. Think of it like moving through molasses, maybe.
Yeah.
This is how the atom actually absorbs energy from the light.
Got it. So the light drives it, the spring pulls it back, and damping slows it down. This wiggle creates a dipole moment, right? An oscillating dipole.
Exactly, $10 Elsers. And the key result here is that this induced dipole moment, pi Bennis, is proportional to the electric field, $1 that's causing it.
And the constant linking them. That's the polarizability.
The atomic polarizability, alpha, yep. It tells you how easily the atom's electron cloud gets distorted by the field. And importantly, because of that damping term.
Let me guess. Alpha isn't just a simple number.
Nope. It's complex. It has a real and imaginary part. And it depends strongly on the frequency, omega Allers of the light. Get near the atom's natural resonance frequency, the spring's natural bounce frequency, and alpha gets huge.
So the material's response depends dramatically on the color of the light. Okay, that makes sense. And the total polarization of the material, capital P, is just adding up all these little atomic dipoles.
Basically, yes. It's a number of atoms per unit volume, not Aller times the average dipole moment. So PE equals N times P2, or 2 equals N alpha E. That Paula vector is our bridge from the micro to the macro.
Okay, now we bring in the big guns, Maxwell's equations. But wait, if the material itself is polarizing, creating these little dipoles, that must mess with the fields, right? We can't just use the vacuum equations.
You absolutely can't. That polarization creates its own charge densities because of positive and negative charges shift. And since they're moving, they create a current density too, J-Baller.
How is G-ball defined?
It's simply the rate of change of the polarization vector ballers. So partial P, partial T$, we have to account for these bound charges and currents now.
This sounds like it could get messy really fast. How did Maxwell handle it?
With a brilliant bit of, well, clever bookkeeping, really. He introduced two new vector fields to help simplify things. The electric displacement and the auxiliary magnetic field.
Ah, dollars.
Yeah.
I always wondered, why invent dollars? What's wrong with just using a dollar?
It's purely for convenience in materials. The definition is $1 is Y's epsilon E plus PT. See? It bundles the effect of the material's polarization right into the definition of dollars.
So it sort of hides the complexity.
It sweeps the effects of those bound polarization charges and currents under the rug, definitionally speaking. When you rewrite Maxwell's equations using dollars again, they look simpler again. They only explicitly depend on the other charges and currents. The free ones we might add ourselves.
Okay, that is convenient. So dollars lets us write cleaner wave equations even inside matter.
Exactly. And that's what we need to figure out the refractive index. We take those Maxwell equations in terms of dollars, assume no free charges or currents, do some vector calculus.
Like taking curls and using identity.
Right. And we end up with a wave equation for Euler. But, crucially, this wave equation now includes a term involving polarization.
Now, if we just plugged in our simple PPE alpha EOR relation, like we did for gases, we'd get something like $2 1 plus N alpha epsilon dollar. But you said dense matter is different.
It is. And here's the absolute key distinction for dense materials. the local field correction.
Okay, what's that?
Think about one specific atom inside the solid. The electric field it actually feels, the electric field isn't just the average field hour throughout the material,
Why not?
because its nearest neighbors are also polarizing. They create their own little dipole fields, and those fields add up right where our atom is sitting. You can't ignore them when things are packed tightly.
Ah, okay. Like trying to hear someone across a noisy, crowded room.
Mm-hmm.
The local noise from your neighbors affects what you hear.
Great analogy. The neighbors' fields modify the field felt by any individual atom. For many common materials, things that are isotropic, like cubic crystals or liquids, there's a specific formula for this correction.
What is it?
It turns out that E local commodial was E plus P 3 epsilon dollar. That extra P 3 epsilon dollar term is the average contribution from all the neighbors.
Doesn't look like a huge term, but you're saying it changes everything.
Fundamentally. Because remember, the dipole moment of our atom is pp alpha E local dollar, so now we have to substitute that corrected local field back into the equation for Peely.
So ppn alpha becomes ppn alpha, E plus P3 epsilon.
Oh,
Okay, I see. P tally is now on both sides of the equation. We have to rearrange it.
Exactly. You solve that algebraic equation for p dollars in terms of hour, then relate that back to the refractive index not using the wave equation result, and when the dust settles,
We get something different from the simple gas formula.
we get the famous Clausius-Mosotti equation, fraction 1,2 plus 2, fraction alpha 3 epsilon.
Wow. Okay, that looks quite different.
Yeah.
Fraction n2 plus 2 epsilon. Why is this the right answer for dense stuff?
Because it correctly builds in that local field effect the influence of the neighbors. It connects the macroscopic measurement non-dollar to the microscopic properties and non-field, but mediated by that density-dependent interaction term. It works much better than the naive gas formula for liquids and solids.
That's a really important step.
Yeah.
Shows density isn't just a scaling factor, it changes the rules. Okay, now let's circle back. You said alpha, the polarizability, was complex because of damping.
Yeah.
So if alpha is complex, and it appears in the Clausius-Mosotti equation, then no dollar must also be complex.
It absolutely must. We write $1 equals NR plus I NI1. The refractive index has a real part, $1, and an imaginary part, non-dollar.
What do these parts mean physically?
Non-dollar dollars, the real part, is what we usually think of as the refractive index. It determines the phase velocity of the wave in the material, CNR, phases equals CNR dollar. It governs the bending of light.
And of the dollars, the imaginary part.
That governs absorption. If non-dollar is positive, it means the amplitude of the light wave decays exponentially as it travels through the material. It gets dimmer and dimmer.
So the complex nature of Nodder directly links refraction and absorption. They're two sides of the same coin, tracing back to that damping in the electron model.
Precisely. The friction that damps the electron's oscillation manifests macroscopically as the absorption of light energy.
Okay, that framework seems solid for dielectrics, insulators, where electrons are bound. Now what about metals? Conductors. The electrons there are free, aren't they?
They are, well, mostly free. They're the conduction electrons. In our oscillator model, this is like setting the spring constant to 0. There's no restoring force pulling them back to a specific atom.
So no natural resonant frequency, omega wheels over.
Mm-hmm.
What does affect their motion when the light wave's E field hits them?
Two things. The driving E field itself and damping. But the damping mechanism is different now. It's mainly due to collisions with the ions in the metal lattice. They bump into things and lose momentum.
So still a driving force,
Yeah.
still damping, but no spring. This damping, is that related to electrical resistance?
Directly, this is where optics beautifully connects to basic electricity. That damping factor, often called gamma, in the equations for the electron motion in a metal is directly proportional to the material's macroscopic electrical conductivity, sigma.
Wow. So the same property that makes copper a good wire also dictates how it interacts with light waves.
Fundamentally, yes. Higher conductivity means more damping for the driven electrons, which means stronger interaction with the light.
Okay, let's use this idea. We have an expression for two angios that now involves conductivity sigma, or the damping gamma. What happens at very different light frequencies, say low frequencies?
Like radio waves. Okay. At very low frequency omega, that conductivity term dominates the expression for 2 and $2. You end up with a refractive index that is large and significantly very complex. The imaginary part, non-dollar, is huge.
And a huge non-dollars means?
Massive absorption. The wave just can't penetrate far into the metal. This leads to the concept of skin depth, delta.
Skin depth.
It's the characteristic distance the wave travels into the conductor before its amplitude drops significantly, usually to $11 of its initial value. For good conductors like copper and typical radio frequencies, delta is tiny millimeters or even less.
So the waves basically just bounce off the surface.
Or get absorbed very near the surface, yeah. That's why metals are excellent shields for electromagnetic waves at lower frequencies. The waves can't get in.
Okay, that's low frequency. What about the other extreme? Really high frequencies, like UV or X-rays?
Now, omega-on is very large. So large, in fact, that the electron gets pushed back and forth so rapidly it doesn't really have much time to collide with anything or feel the effect of the damping, or tzeka. You can often neglect the damping term at very high frequencies.
So the formula for 2 simplifies.
It simplifies quite elegantly. It becomes 2 approx 1.
Mm-hmm.
I make it so.
That's something.
It's a constant that depends on the charge and mass of the electron, and crucially, on another dollar, the number density of free electrons in the metal. This whole constant term is usually written as the square of another frequency, the plasma frequency, omega-2.
So $2 approx 1 omega-2. So, okay, the plasma frequency. Why is that frequency important? What does it represent?
You can think of omega part as the natural frequency at which the entire sea of free electrons would oscillate together if you, say, displace them slightly and let them go. It's determined purely by the density of those free electrons.
And its value determines how the metal behaves optically at high frequencies.
Completely. It sets a critical threshold. Look at the equation. $2 is less 1 omega-2 omega-2 coulomb.
Two cases.
Case 1. The light frequency omega is less than the plasma frequency omega dollar.
Then omega-2 layers is greater than 1, so $2 is negative.
Negative. What does a negative $2 mean?
It means nullars is purely imaginary. There's no real part. The wave doesn't propagate in the usual way. It gets reflected or decays extremely rapidly. The metal is opaque.
Ah. So for visible light, its frequency must be below the plasma frequency for most metals because they look shiny and opaque.
Exactly. For typical metals like silver or gold, omegas is usually up in the ultraviolet range. Visible light is below that.
Okay, case 2. The light frequency omega is less than 1. So 2 is positive, but it's less than 1.
So nullars is real and less than 1.
Yeah.
Wait, the refractive index is less than unity.
Yes. And because nullars is real, the imaginary part is 0, or very small. 0 absorption. The wave propagates, the metal becomes transparent.
It's transparent. Metals.
At high enough frequencies, yes. X-rays, for example, have frequencies way above the plasma frequency of most metals. That's why X-rays can pass through thin sheets of aluminum or other metals. The metal suddenly behaves like a dielectric with an O1.
That's incredible. The same shiny, opaque metal becomes clear as glass if you just hit it with high enough frequency light. All because of the electron density setting that omega-poroidal threshold.
It's a beautiful consequence of the physics.
This has been fantastic. We've gone from electrons on springs to why metals reflect visible light but let X-rays through. Let's quickly recap the main takeaways.
Sure. First, for dense materials, you must consider the local field correction. Your neighbors matter. This leads to the Clausius-Mosotti equation, which correctly relates non-alpha and non-phenol dollars.
Second, the refractive index is fundamentally complex. The real part, non-dollar, gives the phase velocity. The imaginary part, non-dollar, gives absorption. They are linked.
And third, for metals, the interaction is dominated by free electrons and conductivity at low frequencies, leading to skin depth. But at high frequencies, it's all about the plasma frequency. Below omega, opaque. Above omega, transparent.
It really shows how Maxwell's equations, combined with a simple classical model of the electron, can explain so much about how light and matter interact. Amazing stuff. Thanks for walking us through it.
My pleasure. And maybe a final thought for you to ponder. Since that plasma frequency, omega tau, depends directly on the density of free electrons, could we engineer materials, perhaps by layering different substances or creating nanostructures, to precisely control dollars? Could we make a material that has a specifically tuned omega pole, making it, say, opaque to visible light, but perfectly transparent to certain microwave or infrared frequencies? What kind of selective shielding or filtering could that enable?